Welcome to the Humans to Mars session on robots and humans, an essential partnership on the Moon and Mars. I'm Steve Mackwell, and I'll be moderating this session. As we plan for human missions to Mars, we have to acknowledge that humans are great at many aspects of planetary surface exploration, but to maximize mission effectiveness and success, we need to delegate more routine or dangerous roles to robotic helpers, whether it's building up and preparing surface infrastructure for human presence, or supporting surface activities by astronauts, or going places that planetary protection requirements preclude access by humans. And it's not too early to start building capability for such robotic-human partnerships, both in terms of technology and operational aspects, and of course, practice realistic analog environments, including the lunar surface, as I'm sure Clive will remind us endlessly throughout this session. We've got a great group of panelists today. Each will have a bit of time to address the topic of this session from the perspective of their specialty, and then take questions from the audience, just a couple. At the end of the session, we hope to have time to take a few extra questions for the team. I'm going to first off introduce the panel, which will be following from left to right, and then down, up top to down. Introducing the panel today, we have Tomo Usui is a full professor at JAXA's Institute of Space and Astronautical Science. He's also a manager of JAXA's curation facility for Hayabusa, Hayabusa 2, and an upcoming Phobos sample return mission, the Martian Moon Exploration, which you've heard a bit about this morning. In addition, he serves as a JAXA representative of the International Mars Ice Mapper mission. His research interests are in the historical evolution of climate, oceans, lakes, and habitability on Mars. Hakan Svedhem is a senior staff scientist at the European Space Agency, presently holding the position as project scientist for the ExoMars Trace Gas Orbiter. He's been involved in most of ESA's planetary missions for over the last 30 years. He was the project scientist for the Venus Express mission and for some time project scientist for the Mars Express mission. His main research interests include planetary atmospheres, in particular related to comparative planetology, interplanetary dust, and space instrumentation. Laurent Sibille is a founding member of Kennedy Space Center's Swamp Works, where he works for the Southeastern University's Research Association. Passionate about the journey of humans beyond Earth, he's a principal and co-investigator on early technology development projects for NASA mission support, with a focus on prospecting and utilization of space resources and planetary surface systems. He served as the subject matter expert on space resources on NASA's Evolvable Mars campaign team. Recently, he was the lead author of a white paper for the National Academy's Planetary Decadal Survey on the need for data collection at Mars in the next decade to prepare for civil engineering activities as part of human missions to the planetary surface. And finally, and of course finally we have Clive Neal. He's a professor at the University of Notre Dame. He's a geologist with 35 years of lunar research experience who's passionate, to say the least, about having human permanence on the moon and beyond. He led the 4 years effort to produce the Lunar Exploration Analysis Group Lunar Exploration Roadmap, 1/3 of which is devoted to using the moon to feed forward to Mars and beyond. He served as lead chair on 2 separate occasions. He's a glutton for punishment. Is an advocate for the moon and NASA, and has testified to the National Space Council on Lunar Exploration. So let's start off with Tomo on the topic of subsurface ice, which is particularly relevant given plans for the robotic ice mapper mission. Tomo will address the following questions. Why is it important for science and reconnaissance to map ice at the mid-latitudes of Mars? In particular, how does knowledge of ice, location, depth, and extent support human exploration? And how will better knowledge of ice extent inform science objectives like ice coring? Also, what are the biggest gaps in our knowledge of mid-latitude ice for both science and reconnaissance? And how will upcoming missions for the International Mars Ice Mapper help us address these gaps? Tomo?
Yep. Can you hear me?
Yep.
Oh. Thank you very much for the wonderful questions. So it's one of the long-standing issue for the Mars science why we should go to the mid-latitude to look for the Mars. So answer is simple. We now know that there should be a tons of missing water ice reservoir underground. So the number of Mars exploration last decades have suggested that there was a large body of the ocean, surface water, and then some of which have lost to space, but we still do not know where the rest of the water gone. It's still a big question of Mars science, inventory, and distribution of present water reservoir. So the recon of the missing the present water ice reservoir is just more than the scientific topic anymore, because the present water, and if the subsurface ice is there, it is no doubt that we should utilize it for the human exploration, of course, and also the mid latitude is a key for the human explorations. So the high latitude, we have an ice cap, lots of water ice usable, but the high latitude is too cold to support the sustainable human activities, while the low latitude, like the equatorial regions, has high enough sunlight, but it's too warm to sustain the accessible water ice that shallow underneath the surface. So the key question is the missing water. How are we gonna get the information about the missing subsurface water reservoirs? So international partners, including the U.S., Canada, and Japan and Italy, plans the ice mapper missions, and then that will utilize the radar sounder technique to map out the subsurface water ice. The radar sounding use a wavelength infrared spectrometers. It can penetrate, has a potential to penetrate into the depths underneath the surface with the high spatial resolution. So this is simple answers. Is it good enough? I hope it is good enough.
So, Tobo,
Yep.
is that's your you're done, right?
Yep.
Okay, I wasn't just to be sure. Just out of curiosity, how deep will the various techniques be able to penetrate below the surface to be able to detect ice?
Yep. So the ice mapper mission is going to use the L band radar sounding techniques, which has the penetration depth could be like 10 meters or shallower than that. So the 10 meters is pretty much the key, because the if it is like 100 meters or miles or something, it's not the accessible by human explorations. The 10 meters is could be accessible by digging by human exploration. So we are going to have less than the 10 meters, but the very high spatial resolutions. So yeah.
Is there any plans to follow through with missions that would characterize the nature of the ice, such as impurities and things like that, or trying to access it to determine its viability for as a source of resources for human habitation on the
Yep.
surface?
Not only the ice mapper mission cannot tell all the information that you
Yeah.
pointed out, that like which is the state of the ice, state of the water, chemistry of water, because the ice mapper has a special techniques of radar sounding, the radar
Hmm.
techniques that would give us just a faint physical property difference between the rocks and the non-rocks, which could be ice, but just an electric property information. This is not so much great to give us details information. So we're gonna combine radar techniques with the pre-existing information of the neutron data, so the gamma ray data, and also uh, geotechnical properties. So we should combine all of them. But it's the trick is that the radar sounding is only the remote sensing techniques can penetrate into the meters or something. So,
Exactly. Yeah, I was kind of curious to know if there was a more of a longer term plan. You know, once you've identified where the ice is near the surface, whether or not there's actually a kind of a strategic plan for robotic exploration that would then be able to go or be access those zones where it's close enough to the surface to be able to characterize and test technologies and things like that for extraction.
Yeah, thanks. Yeah. So adding to this point that just an accessible ice is not good enough for human exploration, as I said. Like if you go to the ice cap and then there are tons of the accessible ice, but it's just ice. So we don't have any sunlight, not sustainable for human exploration. Scientifically very important, but it's not ideal place for the human exploration. So it's kind of a balance between science and exploration. So
I would say if people have any questions in the audience, have questions, feel free to post them and we will bring them to the speakers. Okay, so let's move on to Laurent. Laurent's going to talk about civil engineering issues for Mars. He's going to address the following questions. Why do we need civil engineering on Mars? I think it's kind of obvious myself, but like landing pads, roads, other infrastructure. So what are the current concepts of operations for landed assets? Where and how close do they need to be placed together or how far apart? Is the current concept of operations planning realistic? In what ways are the challenges of civil engineering on Mars different from those on Earth? And what do we need to know about Mars from a civil engineering perspective before sending humans? For example, you know, how can we use local resources to enable civil engineering, for example, 3D printing for habitats, for roads, for various types of infrastructure, for landing pads? Anyway, pass it on to you, Laurent.
Yeah, thank you. Thank you, Steve. And thank you to ExploreMars to have invited me to this panel and get a chance to talk a little bit about something that not many conferences look at this point because we're very early into this concept of civil engineering at Mars or even civil engineering anywhere other than Earth. So as we know, on Earth, we don't typically send people to remote and extreme environments to live for months or years without knowing something about the place that will host them, and find out where we can build shelters or where we can build the landing strip or roads to be traversed and the necessary infrastructure that comes to with all this. And we think that preparation is even more critical for Mars explorers because they will be really literally cut off from any rapid assistance or rapid resupply from Earth. And the minimum stay on Mars will be significant, calling for good preparation for shelters, especially in the environment, and also to prepare for these first landings. One of the things that we are particularly concerned about is as we have noticed both on the moon and on Mars, the use of propulsive descent by landers basically excoriate or erode the regular surface. And to be very specific for the Mars case, in 2012, Curiosity, using the famous Sky Crane retropropulsion system, showed that there was significant amount of ejecta from the particles on the ground. And they noticed a hit on some instruments. And now we are at a point where probably the state of the art is planning that about 2-ton landers can be sent reliably with the current technology. But at the same time, the human class landers are on the order of 20-ton payload. So so now we're facing very large retropropulsion systems for landing, and it is now critical that we know what's going to happen to the soil under the lander. Not only for the landing itself, which is obvious. After landing, you may have created a large changes in the topography of the landing site. If, for example, it's the first landing and you have to offload a lot of equipment, or your first habitat and where to put it and so forth. So there's a cascade of event that comes with all the logistics of those missions. Now, the current ConOps would basically, look at, well, let's look at a potentially good site and bring most of the equipment on site. But then the ConOps for the subsequent missions is not clear, because now you have all these assets around a landing site, and you have to either prepare for another lander, move a current lander, or protect these assets from the lander that is coming next. And so you quickly come into scenarios where you have to look at how to prepare the soil, what is in the subsurface of these habitats, and then the Martian conditions come into play very quickly, especially in areas where we are very interested in, which are possibly which have subsurface ice, possibly a shallow ice, like Professor Usui was mentioning. And so the knowledge of not only the surface, the type of material that is at the surface, and also the stratigraphy of the subsurface are all part of a common practice in civil engineering on Earth. But particularly for Mars missions, they'll become source of primary information for the safety and the safety of the crew and the safety of the mission themselves. So because we're interested in going to areas where there is significant ice, we also have to ask ourselves the question: what happens to these environments? The surface topography, does the surface topography changes with seasonal changes in pressure? Does the ice underneath move in some ways? Does the topography changes over time? There is also evidence of seasonal changes of liquefied brines in some areas. So all these pertain to actually knowing and really knowing what we're getting into in terms of environment. So one of the things that we focus in our white paper for the National Academy of Sciences is looking at the top priorities of the type of measurements that would be needed in the next decade, because we're looking at sending potentially a human cruise in the following decades, in the 2030s. So landing, knowledge of landing sites is very important, and then knowledge of the subsurface is critical next for where to place habitats, and also knowledge of the surface materials to be able to add in situ constructed habitats or shelters that will come in will come in handy during long exploration phases, where you have radiation that is very severe on the surface of Mars over the long term. You have, of course, the low pressure and meteorites or thermal cycles. So you have these environments that will require a very good longevity on the for the habitats that we are going to ask the crew to live in, and that may require adding surface materials to protect these habitats, even if they are brought from Earth. So, in conclusion, I would say the major challenges are similar to the ones that you face to do civil engineering in extreme environments on Earth or in remote places. But at the same time, they're exacerbated by the fact that we only have a few opportunities over the next decades with the cadence of missions and either remote sensing or on surface missions to actually acquire the data that is needed to understand these before launching human crews, and knowing that they'll be at least sufficiently safe, as much as we can make it for them.
Mm-hmm. So what's the current thinking in terms of, as you say, it's a much larger lander, propulsive landing, significant potential excavation of the subsurface, beyond the mission that Tomo is talking about. Do we need other ways of identifying that, the right places to go?
Yeah, and definitely the use of the remote sensing assets, the current ones, the high imagery assets, and and then hopefully an ice mapper will be critical to have an idea of what is below the surface within the first 10 meters.
Mm-hmm.
And I mean, as we envision operations of excavations for particularly creating the base of a landing pad, consolidating an area like this, or the base of roads and so forth, probably 5 meters may be sufficient to do all of this. So we don't really need to dig to as much as 10 meters, unless we're digging to actually find ice and start extraction of ice as a resource for propellant manufacturing to return to Earth. So I would say that the remote sensing assets that are either current or planned in the next decade will have to be complemented with some surface missions that are specific to a site that we want to send humans to, and the primary mission for that will be to understand the geotechnical characteristics of that site as much as with as high as resolution as possible.
Mm-hmm. We did have a question from Beansy McGee, who asks, are there locations that are better for starting on Mars? Kind of similar to what we were just discussing. Would a location higher up be beneficial, or somewhere much lower be beneficial, since there isn't a threat of flooding, just dust and radiation?
So site selection for missions on Mars is not something that I'm an expert in, but definitely the fact that you're dealing with a very tenuous atmosphere, very often the preferred sites for landing are on the lower elevation, in order to take take advantage as much as possible of the density of the atmosphere for, say, parachutes or aerobraking and so forth. So other than that, there is some protection given by surrounding relief, like maybe cliffs or so, to choose a suitable selection for long-term habitation, where you would have to know maybe weather patterns better to understand where prevailing event come from, possibly where you would want a natural shelter to avoid large dust accumulation on everything over a year time, for example, or several years.
Mm-hmm. Yeah, it seems to me that the civil engineering issues raise kind of questions about what kind of advanced infrastructure you would need to have in place before you put humans on the surface, even for a relatively short mission. You know, obviously you would want to have, it would be desirable to have, as you say, protected habitation,
Right.
but that would have to, you would have to get there. So you would need to have surface mobility capabilities from the landing site, unless you had a prepared landing site, which, so
Right.
there seems to be a lot of issues around what infrastructure is most desired to have in place,
Yeah.
which also raises the question about, do we go back to the same place multiple times because that's where all the infrastructure is?
Sure. Yeah, I mean, as a in any scenario, definitely power infrastructure has to come with the first mission, or it is possible if the concept works out, to actually send a mission that actually implement infrastructure even before humans come there, like you said. So that could be a preparation of a landing zone to have a first landing that is safe. And beyond that, of course, the asset that was used for that could be available for a crew to operate, to make their habitation zone, safer over time.
Clive, you look as though you've got a question.
I don't right now, but I have many questions. But especially from what I just heard. But that's for another time. I'll let Hakan go.
Okay, so let's move on. We can come back with more questions at the end, of course. So Hakan's going to address issues of weather on Mars in a very broad context. He's going to address the following questions. How good are we predicting weather on Mars? In particular, how good are we predicting dust storms? Why is dust storm prediction important? It seems kind of logical, if you've got landers on the surface, human crew, etc. How far in advance do we really need to be able to predict dust storm formation? Is it hours, days, months, years? And how do we plan to mitigate the negative effects of dust storms? So also, how much do we know about the potential for microbial transport on Mars, potentially associated with the dust? And how does the radiation environment at the surface impact the potential for microbial transport? And finally, Hakan gets a lot of questions. Is weather prediction on Mars of more general interest, for example, related to other terrestrial planets? Hakan?
Yeah, thank you, Steve. These are really very interesting questions indeed. Now, about predicting the weather is difficult even on the Earth, with the tens of thousands of sensors and many spacecraft we have circling Earth. So just imagine how difficult it would be on Mars. So at this time, we really are not good at that. But hopefully at the time when we get people there and elaborate constructions, we will have learned a lot. So just to start about what do we mean by weather, really? We can, of course, think about the traditional weather, where we talk about high pressure, low pressure, high and low temperatures, and variability, and winds. But you also have other aspects like dust storms, of course, that are not part of the traditional weather forecast, really. And then, of course, we have also the space weather, which is also affecting the people and everything down on the surface, which includes then energetic particles and ultraviolet light and things like that. But let's start now first with the traditional weather forecast. For doing that, to sort of kick this off, we are using general circulation models, the GCMs, which we call them. They're sometimes also called global climate models. Such models are originally derived from Earth-based models, and they predict the long-term average of pressure and temperatures and atmospheric dynamics. And they, of course, show then the effects of the day to the night variations and the seasonal variations. But as they are really showing the average over a long time, they are not really weather forecast models, but they're a good start for this. They can actually be used then for weather forecast if you also measure parameters on the surface and in the atmosphere, and you feed these measurements into the model in a process called data assimilation. And then eventually this becomes something more like forecast system. However, at this time, we don't have enough sensors on the ground that we can do this. So we have to really improve the number of sensors and spacecraft around Mars to be able to do this. And in that context, actually, European Space Agency, where I am, we are studying a concept now for a weather characterization mission, which we call Fahrenheit. At the moment, it is only in the early study phase, and we have included 4 landers and a low polar orbiter and an aerostationary orbiter, which aerostationary, of course, corresponds to geostationary in the Earth's case, where it appears like the spacecraft hangs above a certain position on the planet continuously. So that would then hang over the landing site, more or less. So, so hopefully we will learn something from this mission, but that's quite far away in time, and it may evolve before we actually launch that. So on Earth, the oceans have a major effect on the weather and the large variability we have on the Earth. And of course, also Earth is a bit closer to the sun, so we have more input from of energy from the sun. On the other hand, on Mars, we don't have any oceans, we are further away. So one might think that predicting Mars weather should be quite easy because these big factors we don't have there. But instead, we have this very unpredictable thing of the dust storms. And we have them at different scale, really small dust devils, we have local storms, we have global storms, and anything in between. And they're all very unpredictable. So the big ones, the really big ones, the global dust storms that we see, they occur approximately, in average, every 3 Martian years, which is about every 5.5 Earth years. But it's very unpredictable. So it's not very regular. The last one, it took place in the summer 2018. That was just after, actually, TGO had arrived in its orbit. So that was very exciting because we could observe it. And we saw also how the dust is then heated up, and it heats up its atmosphere and increases the pressure at higher altitudes. So it has a very major effect. It lifts up water vapor into the atmosphere. So it has major effects on the atmospheric dynamics and atmospheric temperatures. So that's something we want to learn more about. This is also what this mission is supposed to do. We will try to learn more about how are these dust storms actually triggered, and how are they maintained, and how do they eventually evolve and disappear and lay down, settle. So what do we do is, yes, apart from the predicting the weather, of course, it's really important to know when these storms come. Even a small storm can be pretty annoying because obviously what happens in the atmosphere is that it gets very dark down on the surface. And the first thing you notice then is that the electrical power generators you have, that your solar panels, they just don't get enough light, so you get less power. And then they may also actually deposit dust on the solar panels. So even when the storm is gone, you still have a much less electrical output from these panels because of the dust laying on. So you have to sort of figure out a way to clean them from dust after a dust storm. So that's really very important. And we've seen that also in the past missions that they actually have died more or less from these effects. So of course, it's also important for the humans because dust may get into mechanisms on the surface, and they may even get into the habitats of the astronauts, and they may get into the air cleaning system. So it's very fine dust. It's very something you really want to stay out of your habitat. A third point is that during the entry, descent, and the landing, when you arrive at Mars, if you have a big dust storm going on at that time, you have sort of inflated the atmosphere. So you have a completely different environment where you're entering into. So it probably will be very useful to know more about that at the time when you come there, to more optimize your trajectory for arriving down safely to the surface. Now one can think about how far in advance do we need to predict these things, and of course that all depends on the kind of activity and the severity of the storm. So we have not looked in detail really to classify these different things, but it's of course clear that we don't want to take a large endeavor to travel for many tens of kilometers away from the landing site with a sort of a Mars car if we know that the big storm is coming up. So we certainly would stay indoors until that has passed. So that's sort of one example. But even if you're just with a manned activity right outside your habitat and doing something, and these storms are coming, it's really very good to have some, at least as a minimum, a number of hours lead time when something comes up there. Even if it is only a minor thing like a dust devil, that could be quite disturbing. So concerning then the wind, what is important then for microbial transport on Mars, we really don't know very much about that, because the microbes are usually attached to some grains. They usually don't fly around by themselves. They're attached to grain and they're transported with the winds. But the local winds, we don't know how they are behaving really near the surface. That's also something we're going to try to find out with this concept mission we're trying to design now. So that's an important aspect too. Then we have, of course, limited lifetime of these microbes once they get up in the atmosphere, but not so much because of the radiation environment that is harmful for humans on a longer perspective, like several months or so. These are ionizing radiation from X-rays from solar flares, or energetic charged particles from coronal mass ejections, or cosmic rays, for example. But rather it is the UV light from the sun which is acting as a disinfection and kills actually these microbes very quickly, unless they are protected. So it depends on how they move. If they are ejected from the surface where they've been protected during the night, they can probably move quite far before they are actually encountering UV, and then they just in a very short time can be destroyed. But if they land somewhere remote from the site where they were ejected, then again end up in the shadow, they possibly could continue with a life for a longer time. So this is something we really need to study more carefully, because of course we want to protect areas on Mars and not contaminate it with Earth microbes, in case that we have interesting things that we want to explore and find evidences of perhaps past life on Mars somewhere. We don't want to find what we have actually brought to Mars ourselves. So that's an important point. Then in the larger perspective of comparative planetology, which one of my great interests is, why is then it's important to understand weather prediction on Mars. I think that if you look at the Earth and compare Earth, Venus, and Mars, which are sort of the three major terrestrial planets, of course, together with Mercury, but Mercury doesn't have an atmosphere. But there's an amazing difference between Venus, Mars, and Earth in terms of surface pressure, a factor of 100 less at Mars and a factor of 100 more almost at Venus, and huge temperature differences. And if one can set up models that can be so robust that they are trying to predict correct results on all these planets, one would benefit really in robustness of these models. So I think that's something that I think is very exciting to look into for the future. Not easy though, but it's something to try to do.
Okay, thanks, Hakan. What we might do is move on for the moment, and we do have a couple of questions that I will come back to after Clive, just to make sure that we have enough time at the back end. So passing on to my friend Clive, he's going to talk about how near-term activities at the moon can feed forward to Mars human exploration. He's going to address the following questions. How similar are the major challenges posed by lunar and Martian environments for human exploration? How is robotic exploration of the moon helping enable us to meet such challenges? And what applicabilities are there for enabling human exploration of Mars? It's noteworthy that a recent report from the Office of the Chief Scientist discussed the exciting potential of human crew member extracting ice cores at Mars. Does this have applicability at the moon? And if so, what are the challenges doing such operations, and how can the moon be used to enable such exploration of the subsurface? Clive.
All right. Thank you, Steve. Can you hear me?
Yes.
Okay. All right. So I'm going to be reasonably brief because we're getting close on time. And I'm going to start off by saying, in terms of human space exploration, the moon and Mars are the same. They have environments that will kill humans, and the humans will need to be protected from dust, as we've heard from Hakan and Laurent. They will need water and oxygen to be able to survive, and we have those in spades on Mars, from high latitudes, maybe mid latitudes, as Tomo was talking about, and we also have those on the moon. The humans will have to be protected from the radiation, and they'll also have to be protected from micro and macro meteoroid bombardment. So when you look at what's needed to allow humans to survive and thrive off planet, the Moon and Mars are pretty similar in the broad sense. When we get into the details of a thin atmosphere versus an exosphere, thin atmosphere on Mars, exosphere on the Moon, you have the thermal extremes of lunar night, lunar day that are tempered out at Mars. So there are thermal extremes, but they're not as extreme. But either way, the humans will have to, or the systems that go there will have to protect the humans and isolate them, whether that be the spacesuit, whether that be the habitat. So in terms of the similarities, I think the Moon and Mars are very similar, which means by going to the Moon first, and a good friend of mine, Paul Spudis, wrote a book on it, and I shall summarize his book. Why do we need to go to the Moon? And I'll do that very quickly. It's close, it's interesting, and it's useful. It's close by, whereas Mars is a little bit further away. So we send humans to the Moon to learn to live and work productively off planet, so that we don't kill them when we send them out to Mars. That's critical if we want to have a sustainable human Mars exploration program. We need to ensure that we can send them there, we can keep them healthy, and we can bring them back safely. Because these days we are much more risk averse than we were during Apollo. So having this moon, as Kraft Ericke said, if God wanted us to be a spacefaring species, he'd have given us a moon. And we have our laboratory in our own back garden, relatively speaking, where humans can learn to live and work productively in a very hostile environment that can then be translated out to Mars. So the synergies I see, and this is why I think it's important that the Moon and Mars communities talk with each other and collaborate, because the challenges we face in having sustainable human space exploration at both the planetary bodies are pretty much the same. We need to keep the humans alive. We need to be able to live off the land and use the local resources. And as I say, both the Moon and Mars are scientifically interesting, which is the ice core aspect, because there's ice on the Moon, and does that contain the building blocks of life that seeded the inner solar system during the purported late heavy bombardment? Well, the material's there. We need to go core it. We need to bring those samples back. Can we develop such technologies to do that on the Moon that can then be transferable to Mars, knowing that the transit to Mars is much longer? That is going to be a challenge, but we have a laboratory in our own backyard that we can use to do that, to not only inform science, but exploration and potential commercial involvement. And that brings up the sustainability issue of having humans to the Moon and Mars. How do we make this sustainable, and what is our definition of sustainable? Now that's a whole other issue, but I will say that the resources at Moon and Mars will be the foundation for a sustainable human space exploration program to both planetary bodies. And with that, Steve, I'll leave it so that we have time for a few questions.
Well, thank you, Clive. Actually, what I would like to do, I want to pick a question or so from that have come up from the audience, and then step to a couple of questions to all of you about how, just getting you thinking, how robotic helpers, how do robots work synergistically with humans in the various aspects that we've been discussing today? So before that, first I'll ask this question: will the first humans on Mars stay at the lander, like the lunar missions, or will there be a habitat? Will a habitat be constructed, or inflatables be used as it's a matter of almost 2 years? Well, kind of depends. It could be 30 days, or it could be a year. It's still not an insignificant amount of time to be living in a tin can. So perhaps, Laurent, that I think was directed at you originally. I'm sure Clive has an opinion on that one too.
Yes. So the plans are not formulated very specifically, and you're correct. They depend on the duration of stay. But one thing to remember is that whatever habitat you have is going to have to really protect that crew from radiation. One of the issue that you have, for example, with spacesuits is you cannot really put a lot of radiation protection on them, and then if you start looking at the materials that are involved to afford very long-term good protection for radiation on the Martian surface, you quickly run into problems of mass, of launch mass from Earth.
Mhm.
So using local resources to actually augment that radiation protection is a very good thing. No matter what you do, it's hard to imagine, burying a lander, but especially if that lander has to come back home. But a habitat on the side or taking advantage of surface features is important. There's an interesting 2018 paper by Robert Moses that people should read about that.
Mm-hmm. Did you have a comment, Clive?
Well, I just think that as a geologist, I could spend 30 days looking around a lander and be very productive. But if you're there for 2 years, then I think you're going to be looking at, you may want to branch a bit further out and maximize the time, the humans. You have to remember, though, that when the humans get there, they're probably not going to be in their most productive state.
Mm-hmm.
And it may take some time for the humans to get up and build back up to being back in at least partial gravity rather than being in microgravity for the time that it takes to get out there. And that's something that we can't ignore, as we need to keep humans alive, but we need to keep them productive. So reconditioning is going to be critical.
Yep. And of course, basically, as we learned from Apollo, astronauts getting in and out of a tin can with their suits on has a way of kind of filling the can up with dust over time, which is not terribly pleasant,
right,
if not terribly healthy. Anyway, we've got about 3 minutes to go. So let's just quickly step through. So perhaps start with Tomo and then Hakan, Clive, and Laurent for kind of closing statements on how robotics fit in with human exploration. Tomo?
Yep. So last words, I would say that the subsurface is a keyword for the future exploration of Mars, and subsurface is still a mystery and new front Mars. So conventional mapping tools of the previous tools of the visible infrared spectrometer have given us the nice data set with a high spatial resolution mapping, but it reflects just a very thin surface veneer comparable to its wavelength of microns each. So we need next generations and new tools, which could be the longer wavelengths, the mapping tool, and then also the reaching us to a new frontier of the subsurface world. That could be this is a robotic missions, and but it's the good reconnaissance for future human exploration. This is the what I want to say.
Okay.
At the last
Thank
word.
you.
Yeah.
Thanks, Tomo. Hakan?
I think if I just pick one thing, a very useful thing is that humans could actually deploy weather stations on suitable places, which are not easy to pick from distance remotely. So that could be very, very useful for not maybe forecasting weather, but actually measure the state of the weather at any time. So I think that's a very good thing.
Okay, thank you. Clive, last thoughts?
So I think autonomy. You're going to pre-position assets that the humans can use. When the humans land, they don't want to sandblast the assets. They need to, so a landing launch pad needs to be constructed. Okay. Autonomy.
Thanks, Clive. Laurent?
Yeah, and I would add to this that just like on Earth, we, if you want to survey a site like this and understand it, you would have an army of graduate students in geology to send over there for the summer, and what we have are robots, and they're getting better and better in space exploration. So we need to use them early, now, in the next decade, and during the human missions.
Thank you. Well, I would like to thank our panelists for their perspectives today. It's been great. Thank you very much. And I also like to thank Explore Mars for hosting this panel and for organizing the Humans to Mars Summit. Thank you.
Thank you.
Thank you.
Bye.
Thanks, everyone.